कितना सुंदर दुगने होता है जब एफर्ट जाओगे ना तब प्लांटिंग कर लेना ना So, good morning. So, you have left oil, taken crude oil. Okay. So, we just have some recap. Yesterday, what we thought at the CAD. We have tried to understand how the molecular structure or geometry, as well as energy, as well as different molecular properties can be calculated for an isolated system or can be considered some people call it a vacuum, some people call it a gaseous. Okay. So that is a little bit either easy or difficult. We'll see that whether it was easy or difficult with the solid compared to solid state. Okay. So now first we'll start how what is solid state. Okay. So I will go like this. That initially the brief about solid state and then preliminary basis state. Earlier we are initial state is that of state of so those who will not use the solid state will go for the preliminary basis state. And why we will go for preliminary basis state, that will start. We'll study here, and then I will give a brief about forces and energies and equation of motion and integrators. But details will be given by Professor Energy and I will not go and get them. Just I will talk about those parts which will be useful for this issue only. Rest of the part they will go and then they will teach you about the classical dynamics. So basically, I will be concentrating mainly these two guys, Karparinilo and Born Oppenheimer. Okay, and this again, so they are agreed, and I think they have worked yesterday night also to give you hands-on session in the periodic system. Making molecular periodic system a bit difficult compared to you are doing a dog view or some other software. Easy to make it system. So how the different states of matter are there. So if you could start with the solid, the atoms they are nicely fit in the periodic array. Okay, and then if you hit that matter, solids sufficiently, it will melt, and then you get a liquid state. But the atoms not are in their periodic position, they will move from that position and they will randomly move. Okay. So you give this further hit to the system and it will become gas. The gas means the interaction among the atoms will be weaker and they will move very fast. Okay, so then we are calling gas. Now, if you go further, give energy, the gas will be ionized and you will get ion. Okay, an electron mixed, and that is called plasma. That is also another state of matter. Is it not? So, can you tell me what is the next state of matter? Another matter is there. Which states of matter? Anybody? Can anybody tell? What is Bose-Einstein condensate? You know, is a condensate, isn't it not? So condensate, matlab, it is cooled, is it or not? So cool means hot temperature minimum should be okay, isn't it? So basically, that cool, basically what they are trying to do, some atom they are cooled at 0 K, and that therefore the property is really different from the other four state of matter. So that is the Bose-Einstein condensate. Okay. So basically now we are having 5 states of matter. Now that among the 5 states of matter, the easiest way to study is this guy and this guy. Okay, because this guy follows the kinetic theory of gas. That is well developed, so you can calculate all the properties. And this guy also periodic in nature. So you know that they are not moving here and there, so you can calculate. The difficult task is this guy, and the 5th state of matter. So we will be dealing with today solid state. So what is the definition of solid state? I have given this few points, you know already. So they are hot. Just I have telling that they are in a position is fixed. Okay. And they are following the geometry. So how we are adding the atom, so that accordingly there is some name will come to that. Okay. And then solids true. It is not an imagination. Is it or not? It is true. Is it or not? And then if you cut a solid, how do you get? Yes, you will get a circle. Okay. When you will get a circle, the property will be different from the bulk solid. Okay. So there are different kind of solids. Those who are working in the molecular solid, ionic solids, metallic solid, covalent solid, depending on their nature of bonding between the constituted atom. Okay. So this is the example of molecular solid. That is carbon dioxide. You are talking about that carbon water hydrate. Carbon dioxide, if you also can be solid, if you can be used as a what I say, this is called motif or basis of it. That is the lattice, if you can use it. Benzene also can be solid. Okay, this is a molecular solid. Then this is a covalent solid where the atoms are interacting through covalent bonds like diamond, graphene, quartz, etc. Then there will be ionic solid, as you know, sodium chloride you use regularly in your home. These are not for doing the cooking, so those are called ionic solid. And then metallic solid, the metal basically that is also solid. They are basically based on the ions and basically composed of ions and free electrons. Okay. And then the most important thing to understand solidity, you have to understand what is the unit cell. Okay. So unit cell, basically, if you consider this, as I was talking to you, that this is called lattice. What is the meaning of lattice? So if you arrange some point in a plane, and by keeping their neighboring atoms in the same, or I can say, if their distribution of the neighboring atom is following the periodic nature in all the direction, then you can follow the lattice. Okay. So in this lattice, now this is some point is there. In this point, whatever you want to put, suppose you want to put some atom, sodium atom, so you will get a lattice of a sodium metal. Okay. If you put a lithium, you get a lithium metal. Okay. So that way you will put any element of the periodic table, you will get those metal, or if you put some what I say, so if sodium and chloride, lithium and chloride, potassium chloride, so you will get those kind of ionic solid. Okay. Fine. So basically, what I mean to say that atoms in a lattice are periodically distributed. Okay, so we'll take that advantage of that, and we'll try to see that how we can use density function theory in those periodic system, and we can calculate all the structure and the associated molecular properties. Okay, this as I was talking about that in this basically this is a lattice, so you can put a one rabbit there, so you will get a what I say, solid of rabbit actually. If you put an atom here, you will get a crystal structure. Okay. So now basically the unit cell, the definition is like this: that if you suppose you have a big crystal is there, you go on breaking it, until you will not able to break it. So that is basically called the unit cell. And inversely, you can say that if I multiply the unit cell in 3 directions, X, Y, Z, I will get finally reach the crystal structure. Okay. And that is basically defined by this 3 axis A, B, C, and this angle alpha, beta, and gamma. So these 6 things we will define unit cell as well as crystal lattice. Okay, so now you know this. This is a cubic system. This is very easy to draw and very easy to understand. So you can see that how many. You just tell me how many edges are there here. You know what is the edges of a lattice? So how many are there? Okay. How many faces are there? Okay. So how many atom will be there in the unit cell? Okay, fine. Thank you. Okay, so now it is a type of unit cell. Now this is the first one I already have shown. That is a cubic, and this is basically body center. So how many will be there? Everybody agree to that, na? Two. Very good. Nice. So we can go ahead there, and then we can go to the center. How many will be there? The answer is there. You are not reading that, I think. No? You are counting it, I think. So how many there in the face center? Or how you have come to that code? Okay, fine, very good, thank you. So now we'll move this. Okay, so now basically based on this array of this position of the atom and angle and the ABC, distance of ABC, whether they're equal or not, and the alpha beta gamma, the angle. So come up with the 7 crystal system, and from the 7 crystal system you can go to the. This I am not going to read it. You know already. I just say the 7 crystal system is there, and those 7 crystal system can be distributed in the 14 lattice. So whatever you draw or whatever you will produce, they have to satisfy this. They will not go beyond this 14 classification of lattice. That is called Gravis gradient. Okay. So I am not going to tell the details about that because our objective is not to do this. Okay. So now this is the most important thing in the solid state calculation. Okay. So if you can understand the reciprocal lattice, then only you can get the feel of the calculation in the solid state. Because any calculation is done in the solid state is in the reciprocal lattice. We don't do any calculation in the real phase. Okay. Then anybody any idea the why can do the calculation in real phase? I think there are people that they are already working in solid state calculation. That is the only point. This is one of the point. Another point. If you see that the bracket that is what we have designed, is it finite or is it infinite? That is the area of the point what I have shown, it is infinite or finite? Is finite or infinite? I'll come to that. This guy is finite or infinite? Infinite. Is it or not? So basically, you are dealing a theory with infinite system. Is it or not? Or your system is crystal system is finite. Okay. So now that finite system using the theory of infinite crystal lattice, very difficult to calculate in the real. Because where you will cut up, where you will give the cut up, that surface will come to the picture. So basically, that is why generally we do the calculation in the reciprocal lattice space, because where we can take care of the surface area. I'll come to that how we can take care of the surface area. Okay. So basically, your theory is for infinite lattice. Sir. You are dealing with the infinite lattice theory for a finite lattice. Fine. So now I will define that what is the reciprocal lattice. Reciprocal lattice basically, as I was talking about that, whatever the system we are dealing in, this is a real phase lattice. Now, if I do the Fourier transformation of the real phase lattice, that is called so Fourier phase of the real phase lattice, that will be the reciprocal lattice. So how to get that? So that is given here. That if you do the Fourier transformation of a real phase lattice basically will represent y Plane vector. Okay, and the plane vector real phase lattice will be designed in such a way that it is basically I can say it is a collection of vectors. It is a collection of vectors, and those vectors should represent a planar vector, but that planar vector should consist of the lattice of the branch lattice. Okay, okay, fine. Point clear what I told? That I should take some point which will be in the reciprocal phase, and that vector should generate or yield a plane wave, and that plane wave should satisfy the periodicity of a Brazil lattice. Clear? Okay, fine. Okay, fine. So now there is some mathematical what is a boundary condition is there, how to define it. So those things are given, and that if you are having A and B and C is your real plus coordinate, that you can represent in terms of star. Okay, and then you can if it is the R is your real plus lattice definition vector, and then in terms of reciprocal, you can define this as a HKL, and already we know HKL nothing but the Miller indices. You know what is Miller indices? Anybody can help? Earlier we have seen that unit cell, is it or not? That ABC, we have seen, na? So now that ABC, if you take a inverse of that ABC, that is 1 by A, 1 by B, 1 by C. Okay, now suppose you are getting a 2A, 2B, and 2C. Okay, fine. So now if I take the how many times of the unit cell it is going, so that is 2 times of A, B, C. Okay, now if I take the inverse of that, it's 1 by 2. Ratio then 1 by 2, then 1 by 2 ABC. Okay, so now if then what Miller is telling that you take it, you try to make it an integer. So then if you take multiply it, everything is 2, so you will get it 2 is to 2 is to 2. So that is called Miller indices. So what is significance of Miller indices? Anybody? And how we use Miller indices? The solid state. Is it related to the spacing of a? Suppose you have a plane. In the solid, suppose you have a plane. So is there any relation between Miller indices and the plane of the solid? Have you heard about DHK equal to AY root over H square plus K square? Yeah, very good. Okay, so that is the significance of Miller indices. Okay, you not only significance of Miller indices to get the casing into plane, also you can get define as plane. Okay, because when you do the property of a solid, you need the which plane you are going to work. Okay, whether you are going to work plane 1, 0, 0, I will come to the how to define the plane 0, 0 or something. Okay. So now you have got your real place vector and you have got a reciprocal vector. And if you multiply them, you will get a Hx, Ky, and Lj. All are vector quantities, so it is very easy to multiply. Okay. So now this is another one important what I say property of a crystal that is defined by Wigner's cell. This is one of the smallest. As I say, I was talking about the unit cell. This is the but that unit cell directly cannot be applied for in the computation. So that is why people have come with the idea to define a Wigner's cell. Okay, this is the Wigner's cell. How to construct it? It is if you have a surface passing through the middle of the points. Okay, and then you take all the nearest points. That will define your the Wigner's cell. At that Wigner's cell, when you take in the cable, that is called first Brillouin zone. First Brillouin zone. That I will come to the later. Here, this is the first Brillouin zone. This is nothing but the Wigner's cell in the cable. Okay. After that, if you second neighbor, if you take, it is the second Brillouin zone. If you take a third neighbor, you will get the third Brillouin zone. Okay. So it is looking very simple, but it is really simple. Those who will do the calculation in the whole vector space, essentially we always deal with the real space. Okay, so that is it is very difficult to conceive that how things are being done in the case because you cannot conceive the how KPS is working. Only you have to do in terms of mathematics. So now these things when we are going to do the calculation, we will frequently will encounter these. Those who are already, I think you are doing solid state calculation. No, okay, fine. So they will frequently encounter this original picture, first Brillouin, second Brillouin. Okay. Fine. So now, so far I have told you, I have collected the data from these 3 guys. Okay. These 3 books. So if you want to further pursue your research in this field, you can go through this test. Now I am coming to the plane wave, because until you understand the plane wave, we can do that. Can through the calculation in the solid state. In general solid state, we don't use basically, and the atom center basis state, we don't use it. We can use it, but it will be highly expensive. Okay. So you know what is this? Is it or not? This electromagnetic wave. It consists of two waves. What is those? Electric field is there, and magnetic field is there. They are perpendicular. Both are following which kind of wave? Plane wave. Okay. So they are following the plane wave. So already we know the plane wave. Is it or not? And it is a well established that electromagnetic wave is a wave, and it consists of two field, electric field and magnetic field, and they are plane wave, and they are perpendicular to each other. Okay. Fine. So now that if you represent the wave plane wave in terms of mathematical function, it looks like this: e to the power I k r. Okay. So basically, now the beauty of the plane wave is that it is if the k is arranged by means of following the principle of the gravitatics periodicity, you can generate your what I say periodic nature of the solid. Okay. Fine. We'll see that how we can use that. So now I have given some condition of that, how the plane wave, what is its property. So you can see that yesterday also I was talking about that if you have a molecule, and if you know the molecule having a homology gap, okay, is it or not? So now if you arrange the molecule in a periodic array, so that homology gap will be superimposed. Okay, so then you'll get a band. If you say the physicist always deal with the band, a chemist always deal with the homology gap. So that is thing the second part is telling. The in infinite system, molecular orbitals becomes band. Okay, you can do again by hand also. If you suppose you take one atom and then you add another atom, you calculate homo and then you plot, you will get a band finally. If you want to understand that much more in deep. Okay. And now our vector in plane wave function is similar to the orbital exponent Gaussian function. Yesterday we were thinking e to the minus alpha r square. It was there, now that it is a real plus function. Okay, in that case, alpha, what the role was there here? This guy k is that role. Okay, so one another k will take care of the your periodicity of the, but all k will not take care of that. Only those k who will satisfy the periodicity of the balance letter. Only those k will be useful for us. Okay, fine. So now I was just trying to say that what is the advantage of plane wave compared to the your localized basis set. Basically, your whatever the yesterday we used that Slater and Gaussian orbital, those are localized. Is it not? Localized means they are atom centric because all the basis set are on the atom. But here the basis set is not on any atom. The basis set is not on any atom. So basically, what is the advantage of not using a localized basis set? Because in basis set calculation, when you are doing, always we come to that basis set superposition error. Have you heard that word? Basis set superposition error? No. So who has done the calculation in either Gaussian or other? You have never had basis set superposition error. Because why I am telling you, the basis set superposition error is the error. Because what you say that whenever we are generating the wave function in the gas phase calculation or class phase calculation or isolated molecule calculation, we are taking a orbital, and those orbital we are taking a approximated orbital. That is not a complete basis set. Is it or not? So basically, we can never reach complete basis set in that gas phase calculation. So when you are taking an incomplete basis set, whatever the energy you will get, and if you take a complete basis set, you will get energy. Is it or not? So if you take a difference, so that is called the basis set superposition error. Okay, so those kind of error you will not get here because the basis set is not atom centered. Okay, so those questions you will never arrive. So that is another advantage of using plane wave basis set. Now you can ask me that whether this plane wave basis set we can use for the gas phase or not. Is it or not? Yes or no? Is it or not? So can we use this plane wave basis set for gas phase calculation? No. Why? finally, when I will construct my deficit set, you will not see the area itself. It will share the only way. We can calculate. Only we have to put some trick. I will come to that. We have to put some trick. Okay, fine. So now, what is the we have taken that plain wave basis set basically very robust in the sense the convergence is very fast. When you will convert into the K vector in K phase. K phase means it is a imaginary vector, and that grid you can make any discretization of the grid you can make of the K. So you can make a very fast convergence by using first Fourier transformation effective. Okay, we'll come to the later that. So basically, so finally, what I tell that already I have taken that. But now, if you do use this localized basis set, the convergence problem, because if you use this Slater or Gaussian type basis set in this first periodic system, there will be a problem of convergence because the atoms which are there, they are periodic in nature. So their potential is periodic in nature, and that periodic nature of the potential will not convert first if you use the Slater type or Gaussian type orbital. Okay, that is the disadvantage of if you are trying to use that Gaussian or Slater type orbital, in this case, solid system. Okay. So this is the details. I will not go into this. Okay. So now I will come to just why I was talking about that. It should be a potential in a periodic. Periodic potential. Have you heard periodic potential? No, you have heard Lagrange's potential. You have heard Lagrange's potential. You have heard. Never you have heard periodic potential. So now, why we are calling it a periodic potential? Let us understand. Try to do that. So basically, this is the concept of a Jellium model. Jellium model means anybody can tell out what is Jellium model? Have you heard the name of Jellium model? Anybody has used the earlier density functional theory? Anybody has used density functional theory? Anybody? Nobody has used density functional theory here. Any calculation? Yeah. So you have never heard the Jellium model. So that is the problem. You should when you are going to use the density functional theory, the density functional theory has been developed based on the Jellium model. The Jellium model is basically nothing but that they are considering that I am having infinite volume of space, and that infinite volume of space considering infinite number of electrons. So when the volume is infinite, or number of electron is there, and it is basically called electron gas. Have you heard the name of electron gas? We generally got hydrogen gas, helium gas, krypton gas. So that is called electron gas. Huh? So this is called homogeneous electron gas. Okay, and that homogeneous electron gas is there, and that is and that gas has been kept to because you have to neutralize the electron. So yeah, there is a uniform background of positive charge. So that's called the Jellium model. So that Jellium model was used yesterday when I was telling you during the density functional theory. So the local density approximation they are using, I have shown that Slater model was there. They are using the LDA, local density approximation. I was showing that there are different kind of density functional model. So to capture the exchange correlation functional, LDA, DGA. So there one LDA was there. The LDA they used to use this model, the Jellium model. That throughout the system, the density of the electron is constant. So that is basically a model. It is not an actual one. So now if the electrons are there, and electrons are attracted by the ions, okay, to give the system neutral, because all solids are neutral on charge. Neutral, okay, fine. So now let us see how we can understand this guy. So now let us. This is an ion. This is an ion. Electron. Now this is the position of the electron. Fine. So now yesterday I have shown you on the equation electron nucleus attraction. Is it or not? That was minus Z dot square by R. R minus R was there. Let us consider that the effective R. Okay. So now that R is there, but now that if R is getting reduced, if that R is reduced, so what will happen to that? So this R is reduced, so this is the minimum R to the ion. Is it or not? If it is the ion, this is the electron, this is the minimum position. This is the minimum position. So you look at the maximum attraction will be there. So maximum attraction will be there because the minimum position. Now the ion is moving. These are two ions there because they are in periodic. array. Okay, this electron was there. That electron now is moving. Okay, because there is a competition between these two ions to take that electron. Okay, so now slowly, if you R is moving, electron is moving, so R is increasing. So your equation was minus JD by R, Z square by R. So R is getting increased. So your attraction with this ion is getting reduced. Is it or not? Okay, slowly it is moving. Now it will get a maximum when it will be in between these two ions. Okay, so now that the electron is coming closer to this guy. Again, it will be okay. So this way the things will behave in the solid state. But in your molecular state, it is not like that. In molecules, it is not like that. So that is why they are called as a periodic potential. Understand? Try to understand that why it is called periodic potential. And we will take advantage of this periodic potential for the calculation in the solid state. Then our life will be very easy when you use the reciprocal lattice. Okay? Understand? Clear? So that means if then this coordinates I can write is NA1, A1, N2, A2, N3, A3. As all electrons having a three XYZ coordinate. So that I have written in terms of A1, A2, A3. Fine. So now I can write this. I can write or not? Can I write this? V of R equal to V of R plus Rn. That what the electron, what is experiencing the interaction with this ion will be with this ion also. That means if I have a position at V equal to R, if I go to the V equal to R plus A, I will having the same interaction. Okay, clear? So that means my interaction with the electron is periodic in nature. How far I am going from my any ion to another ion, because they all are distributed in a periodic array. So interaction will be the same everywhere. Fine. So I can write this V of R equal to V of R plus R. Fine. So this is the okay. Fine. So we have got a potential which is periodic in nature, and we can approximate the potential V of R equal to V of R plus R. Fine. So now that is not the end, because finally we have to use that concept. So now that Bloch came into the rescue, so he developed a theory. So what he told that if you are having a wave function, just now we talk about potential. Still you don't know what is our wave function in the periodic system. So we have to generate a potential wave function for a periodic system. So we are trying to construct that wave function now. Fine. So let us think about a ring. Okay, as if the ring is repeatedly a one-dimensional system. Fine. And the position of the particle is now here, let us say, and each of having a periodic distance of a, and finally it is coming back to here. Okay. So now, already we have seen this guy. Vx is equal to Vx plus Ma. We have already proven this in the first slide. We have proved that the potential is at the x position and the potential is at the x plus a position will be the same. That already we have proven. Fine. Now this particle is here. Now I am going from here to here to here to here, and finally I will come to here. Okay. So now my function, wave function at psi of x plus a. Let us say that since it is periodic in nature, I say my potential is same. So this particle when it was here and when it is coming here, the original wave function which was here at psi x, that will be changed by a constant j. That will be changed by a constant j. Since we have told that our potential is not going to change. Okay, I will know that the potential will define your wave function. Is it or not? So now I have gone a, then a plus a, so 2a. So if I am having a go, if I go 2a, so it will be j square. If I 3, then it will be j cube. So if let us consider there is n number of a is there. When in our one dimensional crystal, there is n number length is a. A is the each length. A total number of atoms is n. So I will get total length is L. Okay. So my this thing is then so psi x of n a equal to j to the power n psi x, okay, equal to psi x. So basically I started from here. Is it or not? Now, then again, I have come back to here. So when I am coming back to here, then my wave function at x plus na is we are writing j. So basically, it is same wave function only now. So then means my j of n, j to the power n should be 1. J to the power n should be 1. Is it or not? Am I clear here? Is it or not? So I am again back here. So what should be the value of jn? But it is not the normal value of jn. That jn has to be, it is a number of roots. N, therefore that j will have an n number of roots. Okay, and that n number of roots, in mathematically I can express it is equal I twice pi m by n, where m is the integer, okay, or n is equal to L by A. Already I have told what is n equal to L by A. Because L is my total length of the crystal, okay, or n is the individual total number, or it is total complete total length, or it is a number into A. So this is the pacing. So if I use it, so this I am coming to this expression. Okay, so now I have got my psi of x plus na equal to j to the power n psi x, and where j can be represented this way. Fine. So basically, we are trying to introduce periodicity in the wave function through this guy. Okay, it's 2i pi by n. Okay, m is the integer, or n is the L by A. So basically, how nicely you are introducing periodicity in the wave function, you just see. So now I have got my n equal to L by A j. And then I am just doing some mathematical manipulation. I have put that value n equal to L by A here. And then I have defined this guy expression as a e to the power I k. K is a vector, and this k can be represented by twice pi m by L. Okay, fine. So now I have started with this psi x a is equal to g of psi x. So now I have got my value j in terms of plane wave. You see just. So nicely we have got our wave function, which we can use in the solid state. Okay. So now I have got my wave function psi of x plus a equal to e to the power I k psi x. So basically, you can say that the a is nothing but the translational operator. Okay, translational operator. If I use an operator which can translate a function in terms of pacing of the solid. Okay, fine. So now any function which satisfied again further can be written as psi k of x equal to ukx. Ukx is nothing but the periodic function into e to the power chi x. This is all at one dimension we are talking about. So this is called the famous celebrated Bloch theorem. So using this Bloch theorem, all solid state property is being kept. It is a highly celebrated relation. Okay. Now, so the definition is given. The eigenstate, the physics people use this way. The eigenstate of one electron Hamiltonian, because we have told you that always we are always dealing with one electron. Okay, we are always using the one independent electron approximation. Always, otherwise we cannot solve any multi-electron or many-body problem. Okay, so its periodic in potential can be chosen to have the form of a plane wave. There is e to the power ikx with the periodicity. Again and again, I was talking about the periodicity of the Babin lattice, and this guy takes care of the periodicity of the Babin lattice, uk of x, and that uk of x plus a. Already we have shown that this is nothing but uk of x plus a equal to uk. Fine. Up to this line is very easy. Let us go ahead. Okay, so now my plane wave function looks like this. In the earlier slides, I have shown psi kx equal to this. So if you put in a mathematical expression and if you plot it, how it looks. If you plot only ukx, it will look like this. Already we have shown in the periodic potential. And if you put this is basically this is the wave equation, it will like this. So basically, finally we got this expression which can represent a solid array of the atom in a solid. Fine. So far life is okay. Let's move again further. Okay, so now we will try to see that how we can manipulate further this. Already we have discussed the reciprocal lattice vector and this HKL Miller indices. So now what I am trying to do, a Fourier transformation. Okay, by taking the help of the translational invariant of the plane wave. So what I will do here. Now here I am just applying this Fourier transformation. People, how to do the Fourier transformation. It is very simple. You can go from one vector space to another vector space. That is the Fourier transformation. So we have done here. So we are in the real space. This is the real space. So if I do the Fourier transformation, I am going to the G. G is nothing but the set of G vectors, means set of reciprocal lattice vectors. Okay, and this is a coefficient. In case Slater and Gaussian, we are using some coefficient where we are doing the basis set expansion. You have seen that the phi equal to sum of Ci chi I. We are doing that, and the chi I was the basis function, and the Ci was the coefficient. Similarly, here also we are using the coefficient here. Okay, this is the plane wave representation of the plane wave in G vector space, and this is its coefficient. So basically, then already we know this, so we can psi kr. Now we, instead of ukr, we are putting this guy here, and so we are representing this psi k wave function in terms of, you see that all are in k phase. Okay, this is a dummy variable. K minus G is nothing. You don't have to worry about it. It is just a dummy variable, so you can just add or subtract in the wave vector space. There is no issue at all. So finally, we have come out with a relation, and that psi k of r equal to sum over G, all the G vector states, and the coefficient of that plane wave, and then it is over I k minus G of r. So that is my life now. Let us go ahead. Okay, so now Bloch theorem can be proven in another way. So just you can play with the dummy variable. Earlier I have shown you with the ring, so you can prove in different way. So just you can do that way. So let us have a psi of k plus G of r. I can write this guy as a summation over G of state, G of state. Okay, and then this is the coefficient. This k minus G dash plus G. If you see that G prime, double prime, just if you, this same thing. It is the same thing, you just see. Is it or not? If you take the minus G here and this there, so you will get this. So I am just rearranging it here. Okay, so if I rearrange it here, I am writing here. Then this it was the k, what was there. So if I rearranging here, so I am just rearranging here also. So here I am rearranging. I have got G double dash, then k minus G double dash I have got, and now here also I am rearranging. If you just rearrange this guy, you will get this way. Okay. So now if you further rearrange it, you will get this factor and this factor. Already we have seen in the previous slide that this guy is nothing but the UKR. Okay, so basically this is not so psi k plus G of r equal to psi kr. Okay, so basically how nicely we can play with the reciprocal lattice vector, and we can shift our lattice plane from one vector space to the another vector space. Okay, so now this idea, if I use here my original target, that is H psi k equal to Ek psi k. Okay, so now that if I change my psi k to psi k plus G, so I will get E k plus G, psi k plus G. Now already I have shown that psi k plus G is nothing but psi k. Okay, so I will just keep that H psi k equal to E k plus G psi k. Okay, so this energy now I can write E of k equal to E of k plus G. So I can use as many as number of reciprocal lattice vector now, according to my requirement. That suppose I want to calculate some energy or something. So how much, what is the amount of k vector, or I can choose, or what is the number of plane wave I can choose. So I can define that way. So you see that now, how we have started there using the plane wave, and how we have come to the how the plane wave, the k reciprocal lattice vector can be linked to the total energy of the system. Okay. So the theoretical proof is now done. Okay, complete. Now we'll so move. Another idea that this is a very important thing, because if you have a summation of del of k, how to convert to the integral? Because almost all the calculation we generally do in the either integral or differentiation. Right? So if I can convert my mathematical function in terms of integral, my life is very easy. Then integration is very easy to do. Whatever the large integral is there. So that basically one relation is there. From this relation, we can convert to the sum to the integral. Okay. Now, what I was telling about that point is written here. So, what Bloch theorem has given to us. So, if I am to calculate a solid in the real space, I have to take a large number of wave function. Large number of wave function. Na? Okay. So basically, what that guy has done, you need not to take a large number of functions. You take a small number, limited number of functions. You take a large number of planar. Large number of planar, but you need to take a large number of wave function. Okay, the large number of k points means a large number of plane waves will take care of your large wave function or a long wave function. Okay. So now you see that there is no error due to basis state. Okay, because the basis state is totally independent of the atom. Here we are not talking about anything about atoms. So far we are not talking about anything about the atom. That this plane wave is dependent on the atom. Is it or not? So this is another thing. I will just give a brief. I will not go to the details. That a lot of people always worry about the band structure. The band structure. This is a very simple band structure has been drawn. So many graph curve up and down, crossing here and there. Basically, it is a very simple. If you see that this E already we have shown that E k is equal to E of k plus G is the equivalent. Okay. Now you know that energy E is equal to half mv square. You know that. Okay. So that mv square, if I convert in the momentum case, it will be p square by 2m. Agree? Is equal to p square by 2m. Now in the P, if I use the relation h cross k, P is written as a h cross k. And then if I convert this, this is the instead of h cross k, so my k is now it is modified k, that is k plus g. So you will get h cross square k plus g square by 2m. Fine. Now this k follow the dispersion relation. Dispersion relation is nothing but energy related to energy is not independent of wave vector. Energy is dependent on the wave vector. Okay, so basically E is not E, it is a E of k. Okay, and that k can be plus or minus. K can be plus or minus. And now here we are dealing with the periodic system, and that k can be from pi a to minus pi a to 2 pi a to minus 2 pi a. This way things will go for the real phase as well as reciprocal phase. Reciprocal phase means it will be just inverse of that. Okay, so now if I do that, so pi a to minus pi a, if I plot this guy, I will get a parabola. It is a parabolic type of equation. I will get a parabola. If you go for this second billion zone, that will be this guy will be there. This way you can go on, but we don't need to go beyond third band because we don't get much information after third band. Almost all the information is we get in the first billion zone. Okay, so this way if you do that, you will get a band structure of any solid. Okay, so now just this I have brought from the slides of Sobhana from GLCSL. He is having a very good presentation on this. You can also have a look in a presentation. So basically, just to give a view that plane wave looks like this, or your Gaussian orbiter looks like already yesterday I've shown, and how they can be used for solid state calculation. Okay. So now, what is the advantage of plane waves? This also I brought from Savannah. That is easy to take derivatives, plane waves. It is the way IKR. So you can take easy derivative. Okay, orthonormal, no overlap on because there is no overlapping of the orbiter. In case of Slater and in case of Gaussian, there is overlap. So there is no overlap. Okay, just, I was talking about the independent of atomic position. It does not see the atom is there. Okay, so the plane wave does not have the basis set error. Fine. It is a no no assumption about where charge concentrated. Okay, but when you are doing a Slater Gaussian, there is a that power point is there. Fine. Is it as I was talking about that? Easy to control convergence with respect to size of basis. Huh? So only one parameter E card. That is energy card. I will come to the later. Fine. And I was talking about that can take advantage of first Fourier transformation. Yeah, if you can go from R plus to K plus, your life is very easy. Okay, you can do very fast calculation. So that is what the guy is smiling. Okay. Now, how actually grid is being created in the space? Okay, so already you have seen that our wave function is like this. That this I have not used that. This is a volume of the cell. While you are working, that volume of that cell because you have to normalize the wave function because a good wave function or a good eigenfunction should be true Hermitian Hermitian. Is it or not? So that to satisfy that you have to use this normalization. So now this you can take this grid point as much as possible according to your requirement. But you have to use some cutoff. As I was telling you, you cannot go for infinite k because your computational cost will be highly huge. Is it or not? So that, but we cannot arbitrarily cut k. We have to choose some criteria how to cut. So that is that E cut will come. So I will discuss later. So this is our existing Hamiltonian. So here if you see that it is general, the psi can be planar basis set or psi can be Gaussian or Slater or atom center basis set. Okay. Now, so basically, yesterday also I was discussing how that psi can be constructed, because we are taking the help of the density here, or either way we can take. Okay, if you are going to Hartree-Fock, you are going to a density functional theory. This is your Hamiltonian. So basically, you are using the Hamiltonian. Yesterday I forgot to ask the question. How do you mean by self-consistent? Anybody? Because whenever you are doing any calculation, quantum calculation, that is one of the criteria, the self-consistency. So what do you mean by self-consistency? Anybody can volunteer? Anyone want to volunteer? Then the energy difference is not there. So that is one of the point. But actually self-consistent, what is the meaning of self-consistent? No. Yeah. Acha, Ragivul can say. Acha, okay, Ragivul, let us. And wherever the left hand side and the right hand side, like you are using the input as the for the equation, and effectively you are solving that variable. That and when it satisfies the left hand side, right hand side, then is the time that it is called the statement. Good, correct. Yeah, basically, that is the correct thing. That basically, when you are trying to solve a problem, and if the problem itself is a solution. Got my point? What I told? If you are trying to solve a problem, and the problem itself solution. Confused? Confused. All right. Okay, I'll tell that. So basically, what you are trying to solve, you are trying to find out a true function. You are trying to find out a true function. Is it? So that is for that you are using a operator, Hamiltonian. This Hamiltonian operator will try to find out a psi. Now this Hamiltonian, this itself consists of this psi. You are trying to find the solution for this problem psi, but that psi already involved in this A through this guide. Enough R. So the enough R is nothing but the probability density. Is it or not? Clear or not? Not clear. Problem itself is a solution. Is it or not? The problem was psi, and that psi is already with whom I am trying to help to find that psi. He is already involved, or she is already involved in this Hamiltonian. So then, in that case, what you have to solve? You have to solve it iteratively. You have to solve it iteratively. So you are giving a trial psi, a trial n of r, and then you are doing iteration until my final data and the just preceding data should convert. Understood? So that is the meaning of self-consistency. Okay, clear? So problem is the solution of the okay. Fine. So now that again I have shown that how these things already yesterday also I have shown initial guess, calculate the Hartree contribution and exchange contribution. So now yesterday Priya was asking what is the difference between effective potential and whether they are same or not. Okay. So now that pseudo potential and effective potential or effective core potential, there are different kind of potential. Okay. Now in which context you are discussing, that is the important thing. So if we are considering an isolated cluster system, that is called effective core potential. Okay. Now when you are talking about a solid state, that is pseudo potential. And now when you are talking about this guy, this is effective potential. Okay. When in Hartree-Fock also, Hartree was considering that in each electron is experiencing the average potential by all electron, including that guy itself. So that is also called effective potential. So in which terminology you are defining, that way your effective potential will be defined. Okay. So here also it is called effective potential. Okay, because this thing, if you add plus, if you add the kinetic energy, you will get the quantum operator. Okay. So fine. So that what I was talking about, that how this guy, that why psi is the problem as well as psi is the solution of the Hamiltonian. Okay. So that is why you are solving it iteratively, and it is called self-consistent. How much time I am having? Very good. Very clear, very clear. Okay, fine. So now same thing I have just so it is also I think by a board from Solana. So very nicely prepared the slide. So already that's same thing. Here you see yesterday also we have constructed the Fock matrix type of thing. Here also similar matrix you can construct. So basically again you see that this is it depends on the matrix size, on the how many plane waves you will be taking, and from that number of plane waves how you can define your basis. And accordingly, your requirement. So, how much accuracy you want? What you are going to get? You are trying to calculate a band gap only. You are going to calculate some other thing. Surface energy. You are going to calculate that total energy. Accordingly, you have to choose your basis. Okay. So you are going to calculate optical property. So when you are going to calculate the optical property, its accuracy should be very high. So in that case, you have to go for it. When you are going to calculate a band gap, the band gap is related to optical property. So you have to go for a very large K. Okay. So again, I just that I was discussing that how to choose the K, where I should cut my K. So I cannot do just no, I like it, so I will just cut it here. Okay, so that way we don't do this here. So there is a prescription is there. That prescription is this is basically this is called E cut, energy cut. You just see, I want to cut K, but I am using the terminology E cut, energy cut. Why I am using the terminology E cut? As I was telling you that energy here is energy dependent on K, or energy is a function of K. How it is the energy function of K? You see that this energy is nothing but the h square K plus G square by 2L. So G is a reciprocal sector. So basically energy depends on the K. So if I cut E, automatically I can control this guy. Is it or not? So now this is well defined. This E is well defined. So I can cut. So now accordingly E cut. Later on, we will see that some data is there, result is there also, that how you can affect your energy. Okay, so accordingly I can use the cutoff, and I can control my computation time as well as my computational system. Okay. So now, just I was discussing about that part, unit cell. Okay. So and that we are talking about that whether we can use a gas state calculation in the theory system or not. Digital. So that now we have got some unit cell we have got. Okay, so now unit cell we have to so I have to represent a solid. Okay, so now unit cell is so small. Okay, it cannot capture all the properties of bar. Is it or not? So I have to give a feel of to the unit cell that you are basically repeating the solid. So for that, those who have done Volga dynamic simulation, anybody has done Volga dynamic simulation, classical Volga dynamic? You have done. So there you have used periodicity. Periodic boundary condition. Why you have used periodic boundary condition? And for the continuous movement of. So basically, you suppose you are taking 500 atoms. Is it or not? But 500 in generally one drop of water molecule also contains a number of molecules. Is it or not? So basically, you are far from the 10 to the 23. You are only 500. Already says 1,000. 1,000 and 23 very less. So then what you are doing, you are using periodic boundary condition. So that it is giving the as if the molecule is extended on all the sides. That is the funda. Is it or not? Here also the same thing. This guy, I think, what is his name? Von van Karman. So he gives the idea about the boundary condition that if you are having a 2-unit cell, okay, so and that you can represent it like this. That you are having a unit cell of suppose A is a Cushing, and you can take a 2A, and then you can just expand that unit cell in terms of supercell. So basically, supercell is nothing but what I say, it's a representation of a unit cell in multiplication or in repetition. Okay, but that repetition should be in all directions. Okay, otherwise there will be anisotropy. Okay. Sorry, I have told anisotropy. Now tell me what is anisotropy? Any idea? Any?
Anisotropy means same in all directions, all but anisotropy means there is some difference.
In which? In what?
Composition of phase.
Composition of phase. Okay, now I have water. This water is isotropic and anisotropic. Water is isotropic and isotropic? Isotropic. Why? Same what? No, definitely we'll see same molecule because it is a water only, so we'll say molecule. Some property you have to say. So let's say some density. Density. Isn't it? If wherever you go in water, it will be same density. Now, let's say 1 gram per second. But in case of solid, it will have same density.
It's pure solid, like pure single component solid, then different.
But in because solid is having a one unique property that is called plane. That is called plane. The arrangement of the solid, if you go this direction, the plane is different. So that is why solid is called arrangement. Okay, fine. So now, so that guy has given the idea that if you use a periodic boundary condition, you can repeat the unit cell in all the direction, and you can represent the solid, and that is known as supercell. Supercell, you have heard the name of supercell? Anybody has done work on solid state? So yeah, supercell. So what is the definition of supercell? Repeated unit. Is it a repeated unit of what? Unit cell.
Yes.
Fine. How much you can repeat? Is there any criteria? How you are defining your supercell? The 2 times repeat or 3 times repeat for time. Right. Fine. So I'm not going to discuss that part. So now thus I want to say that if real place your unit cell is A and a supercell, let us say only 2 unit cells are taken, that supercell is 2. So then you can define a reciprocal place. Your first place, reciprocal place always defined in terms of Brownian. So I can define this. I was talking about that. You can go to the k vector pi to by A and minus pi A. Okay. Similarly, if you have a supercell, it can go in the reciprocal place. It will be minus pi by 2A and plus pi by 2. You can go. And then I was discussing about how you can construct that nice structure. This I am giving you just to give a feeling. Just don't do the arbitrary calculation. Software is available, but all things having a basis. Just it is not calculated that yeah, if I do this value, it will do this. Not like that. Everything having a physics, is it or not? So that is why I am giving a feeling that what you are doing the calculation, everything comes from the physics, and that physics how it has come from the very basic thing that I am just trying to give you the information. Okay. So now when you are calculating that automatically, since you are calculating the k vector, k pace. Okay. So how I will choose the k? That question automatically will come, is it or not? In case of splatter, you are just choosing how many Gaussian I will use, how many splatter type of orbital use. Now your question, you know, you are already identified planar. Okay, but now the key, how much I will go, is it not? There should I should put some restriction there also. Okay, so now people are using the different kind of. I'm not going to take details here. So there are different kind of this one pixel point is there. This is the most popular is the Monks pack. This is because why it is anybody has an idea why it is used most pack? Point.
Yes.
It is very simple. Very simple. It is a very homogeneous type of thing. This fishing. This is the only K-point distribution in the maze or in the grid, you can say. It always gives the homogeneous distribution. Okay, so your life is very easy to for the calculation. So you can first go to the convergence. If there is a distribution of K some little bit erratic, your conversion will be very slow. Okay, so that is the funda. Now I will go give some data, share with you some data that how we can use this. Basically, this is an example of iron, simple iron. This is LATIC. So we have done some calculation, and we can show that if you plot this total energy versus volume, you will get this. And from there, you can calculate the lattice constant. Suppose you have constructed a arbitrary any solid, but can you construct any solid arbitrarily? When you are yesterday, Rogi was showing you one molecule, water, is it or not? So he is showing that let us start with the 115, and then you give optimization and counter. So just arbitrarily we are making the water molecule, is it or not? And water molecule can stay 115. So here we cannot make like an arbitrary because all are periodic in nature. So that already, if you see the CI file, you understand, na? CI file, all the lattice constant is already given. So you know all the lattice constant. You start with the lattice constant and you can get this plot very easily. It is very, I think 5 or 10 minutes you will get this plot. Okay, so for solid life is very easy compared to the liquids. The liquid life is very complex. Okay, and then you can calculate this all other things, bulk modulus. Those who are interested using this equation, I'm not going to the details of that. Then I will show that you have to take. There are different kind of functional. Mostly popular is the PB functional, Pardue, Barge, and adjoint hop. And here also you can take a dispersion correction and solid also. And then vibrational frequency also you can calculate here. Here also you can calculate 0.9. Whatever things you are calculating in the accelerated molecule system or cluster system or gas system, you can calculate here also. And then I'll show you an example. That example I will go here. Whenever you are using some calculation in solid state, so you have to validate your methodology. Suppose in case of gas case, you are using BTV, we are using 631 Jogibul was showing. Okay, and then I think you have done the dimerization of the benzene. You have done dimerization of benzene. You got a dimer of benzene. It was very close. Very close. What is the basis state you use? So in that it has got you got a dimer. Benzene. What is the distance? So you have not calculated that. Fine. Okay, let us forget about it. So whenever you are doing some calculation, you should always validate your methodology with the reported literature or experimental data. Fine. So here also we have just validated the result for iron. And then this is important. You see, now I want to calculate adsorption energy of hydrogen molecule on a surface. Here I want to calculate adsorption energy of hydrogen molecule on a surface. Suppose I have an iron, and in that hydrogen molecule is getting adsorbed. So how to calculate the adsorption energy there? So basically, it is nothing but the interaction energy of hydrogen molecule with the surface of the iron. So for that, I have calculated the surface. Fine. So I have taken, I think, 4 or 5 layer surface, and then what I did first, I have done this optimization of the total molecule. Slab was there, hydrogen I have kept in a box. It is there, and then as per the DFT protocol that I have used PBE functional. Okay, and then I have optimized it, and then from there I have got a total energy. Fine. So this is the total energy of that. Then I have not put any hydrogen, only iron slab is there. I have done the calculation, optimization, and then that energy is there. And then for hydrogen molecule, I have done the isolated hydrogen molecule. I have kept in a box. I think Rogi will show you how it can be calculated. Okay, very interesting, but you can do that. And then I have calculated this adsorption energy. Basically, if you see the yesterday, you have calculated the dimerization energy. It is the same equation only. Is it or not? Only the terminology is different. Right? So you can calculate the adsorption energy of any gas molecule. So what is the importance of the adsorption energy of gas molecule on its surface? Any importance is there? Why I am calculating the adsorption energy? Have you come across any article, anything that people are calculating surface? Adsorption energy of a gas molecule on a surface.
So if the adsorption energy is low, that means the molecule will easily.
Even simple, I can use as a storage material, na? Is it or not? Simply, I can use the storage material. Any kind of storage, whether CO2, hydrogen, or any gas I can store. If the adsorption energy is very high. Is it or not? I can store it and then later on I can heat it and I can release it. Is it for my so that is the importance of this guy. Okay. So now here also I have just shown that how the adsorption energy varies with the distance. Basically, if you see that when the hydrogen molecule, it is coming from the top, it is getting dissociated. So this is also another application of the surface. So if when you are doing the hydrogenation reaction, you want to make cyclohexane from benzene. So you have to do the hydrogenation of benzene. Is it or not? So how will you do that? You will give some hydrogen molecule, hydrogen, no? Is it or not? And you use some surface, a catalyst. Is it or not? And then you put the benzene. Is it or not? And then that hydrogen will get dissociated. And then benzene out of the double bond is there, that will get dissociated. And that guy will come and the same. Okay. But if you don't use any catalyst, you will get, suppose you are putting the benzene gas in a hydrogen gas, you will get any cyclohexane? You will get any so much concentration of hydrogen gas you put. You will get anything, anytime cyclohexane?
But the energy is so high.
But you will get. I don't feel it. So that is the importance of the surface. Okay, so that is why I am showing this catalysis for the practical purpose. Okay, I think Raghubu will show something. Then this is basically now that the hydrogen what was it is getting broken. It is just it can have a choice to sit. It is not that you will choose as anyone. So it can choose, and there is a position is that top the metal. It can position in the bridge position between two metal atom. I mean, it's basically those are iron atom, and it can cross the tetrahedral. When there a hole is there, it can sit there. Fine. How many times? 48 times? 5 minutes. Okay. So that is another example of hydrogen molecule. This is a tungsten surface. I have shown that basically. Then absorption energy also you can calculate. Absorption energy is basically different from the adsorption. What can you tell what is the difference between adsorption and absorption?
Adsorption is surface phenomena. Absorption is like
Good, very good. Thank you. Okay, so now if you are putting an hydrogen atom in the bulk, yeah, okay, this is a tetrahedral and octahedral hole, and you can calculate the same type of equation, only the energy is different. Okay, okay, and then you can calculate and you can get that energy here. It has been, this is the experimental data, I think, and this we have calculated. This is published already. A lot of people also have published. We have also published. Okay, so this is the result. So just I'm giving the, and I want to show the absorption energy of iron is positive. This is positive value, is it or not? So this is absorption energy iron 0.19 and this is 1.04. So from this, what inference you can draw? This is positive value, is it or not? So what inference you draw? Solubility of hydrogen will be more in tungsten, or solubility of hydrogen will be more in iron. Sure, no? I'm also getting confused. So iron will be hydrogen will be more soluble in iron compared to tungsten. Correct, exactly. That is why tungsten is being used in the fusion reactor. Have you heard about the fusion reactor? You know fusion reactor and in the IEA program, because this project we are working for IEA, so that is why we have done this calculation. So they wanted to know that why tungsten can be chosen for this plasma. That core is there. So in the core, and there is a high temperature. So after that core, there is a different layer of that. So at the end of layer is the tungsten barrier is there. So the tungsten barrier is there is using. They are trying to find a material which have the lowest permeation of hydrogen. Now there is not only hydrogen is there, that TCM is also there. That is radioactive. Basically, it is basically for TCM. So now, so for that materials, we have to develop a material which is having a least permeation. So least permeation is possible only it is having least absorption. Is it or not? Once it is absorbed, automatically it will try to permeate also. No? So and that kind of context it was there. So tungsten is used there. Usually they are using tungsten, but they try to find out a alloy materials which have got better than the tungsten. Okay. So this is the energy cutoff I was talking about that I'll share with you result that if you do the energy cutoff at different value, if your cutoff is less, you see that energy is here. So finally, your cutoff, if you go beyond 450 to 500, slowly it is getting converted. So when you are doing any calculation, you should do a calculation like this, and then you should choose your E card. So that is the funda here. Okay. And then here also here we have shown for K point also. You see that K point, if you get less K point, it is energy is very high. After that, if you go that around 8, after 8, I think it is got converted for this system. And for this is a W, I think tungsten was 16, the tungsten was 54 atoms. So in this case, it is getting converted around 6 K point. Okay. So this you have to do by your different calculation, and then you have to plot it, and then you. But you should always do. Fine. So then this is how to calculate surface energy, as I was talking about. You can calculate that. So you have a 5 slab is there, so you can calculate the surface energy of the 5 slab. Okay, and then you can you know the total number of atom in that slab, and then you take the single atom energy. And then if you take difference and divided by 2 into A is the area of the surface, so you will get a surface energy. That also gives you very good information about your stability of the surface, as well as whether you have reached the convergence or not. Okay, this all are practical problem when you solve it. And this Rahul was in BRC, so at that time he did the calculation. So he for this I think for copper, he has taken a supercell 2 into 2 into 2, and then he also the K point size. You see that. And there is a, after 3, the K point size is converted. So you can, in case of tungsten, we are showing it is for 6 and 6, and then it was for 8 and 8. Is not. So in case of copper, you see that is only 3 and 3. So if it is a 6 and 6 for tungsten, I will use 6.6. Unnecessarily, it is not required to use for copper. No? Otherwise, you cannot do like this in copper. I have got convergence of 3.3. I will use that 3.3 and 3 into 3 into 3 and 3. For tungsten also, so you will get a wrong result. Huh? So for each element, you have to come up with a validation. So always do the validation when you are doing the solution. So same thing, this ECAT also has been done by Ragibul, and this is the result, and the convergence is coming after, I think here, I think 400. Okay. So now catalyst, I was talking about, already I have told, I am not going to take the details that what do you mean by catalyst? Anybody? What do you mean by catalyst?
I think something can lower the emission.
And then he will remain unchanged. He will not participate in the.
I will not participate.
Isn't it not? Fine, very good, nice. So that is only I have shown here that this is the activation energy as you are telling, and this is the free energy of the reactant and the product. Okay. So now if I use a catalyst, what will happen? This activation energy will go down. That is I was telling about. If you just take benzene, and you just take hydrogen, that activation energy is like this. But now if you don't take surface, okay, so if when you are taking surface, this guy is coming down. Because what are the transition state complex you are making, it is highly energized. So it can easily convert to the product. Is it or not? So basically that is why the catalyst is basically accelerating your reaction. Okay, and then if you accelerating your reaction, these things will also go up and will be very high. And so you will get your favorable product always. So for designing, so you need to have a surface phenomena. Okay, so you should always calculate the surface phenomena. So that is a thing. That is a thing. So already I have talked about that. When there is absorption, whether it is a physiabsorption or it is a chemiabsorption, that also you can calculate. Okay. So if it is around 10 to 40 kilojoule, it is physiabsorption. If it is around 100 to 500 kilojoule, it is called chemiabsorption. And then this I have bought from somebody else. This is a very good photograph I like to share. That suppose you are having a magnesium oxide surface. If you are having a CO2, this guy is having an energy of what, 2 kilofarad. So it is a physiabsorption. But you see that if it is SO2, same surface. If SO2 is there, 25 kilo. Same surface, if you are having SO3, 50 kilofarad. So you can do surface calculation and can say that whether my whatever the use the storage or some catalytic reaction, I can choose my surface. The surface is very important in the catalysis. Okay, fine. So now I think this is final. This is just a representation. In palladium, mostly hydrogen is absorbed. Palladium, you have heard in general we heard about the word solubility in liquid. But in case of solid also, there is something called solid solution. So this is actually that is the thing. Hydrogen is basically soluble there, basically highly soluble actually. Okay, that I wanted to show you. I think that is the end. Now there are few good articles as well as good book are there. You can I think Fetal, I think a lot of people have read it. So you want that to go, so you can do that. So I will stop here, and then after that, T will go for pseudopotence. Okay, fine. Any questions so far? Otherwise, we can join for P, isn't it?
Yes, sir.
Align.
Yes, sir.
You got that. Please, please. Then I will.